Okay, 1 would be the largest. Why? Because I am normalizing it with the maximum one. And so the one that corresponds to the maximum frequency will be 1. All the others. What would be the smallest one? -1 or 0? Which one? What would be the smallest TF-IJ value? Zero is the answer, yes. It's not -1. It is 0. Okay, good. So this TF, the term frequency vector for a document will be between 0 and 1, and it will be values like 0.1, 0.2, maybe 0.0, but one of them is going to be 1.0. Definitely. Okay, definitely is going to be 1.0. So this is called term frequency vector for a document or query string. So this is going to measure only the most frequently happening terms for a document. But the thing is that I know that there are some words, for example, at the university environment, I think the term class happens a lot. So the term class, because at the university environment, almost all the documents will contain this word, or student maybe. Student will happen almost always. So what do I do? So I mean, student will happen always, and it will happen very frequently. So this is not very informative about the document, because it doesn't mean much in terms of finding the similarity between two documents, because all the documents contain student. So what am I going to do is I am going to find the value of a term that is good for differentiating between two documents. Okay, so that's what I'm going to do. It's going to be term weights inverse document frequency. Terms that appear in many different documents. Okay, we say that terms that appear in many documents are less indicative of overall topic. Student term, the term student happens a lot in the documents of Gebze Technical University documents. So it is not indicative. Okay, so I am going to define this. DFI is the document frequency of term I, that is the number of documents containing term I. Let's say I have 10,000 documents at the Gebze Technical University website. Okay, so I is student. What is DFI for student? It is 10,000, because I see the term student in almost all the documents of the Gebze Technical University websites, internet pages. So DFI number for student is very large, and we don't like large numbers because they are not good they are not very informative about the document. So that's the document frequency. There is another term, inverse document frequency. Inverse document frequency is this. N is the number of documents. DFI is the document frequency. I divided by this one. So what was the DFI for student? 10,000. There are 10,000 documents. 10,000 over 10,000 is 1. I take the logarithm of it. So that means that smaller the number, okay, smaller the discrimination power of that term. Okay, if DFI is large, it could be as large as n, right? So this number could be as small as 1.0, but it could be very, very large. Let's say there is a term, let's say perplexity. The term is perplexity. I don't think that we will have the term perplexity in any documents of the Gebze Technical University website. Maybe in one of my slides, maybe. That's it. So perplexity happens once or maybe twice in the Gebze Technical University documents. So there are 10,000 documents, and perplexity happens 2 times. So this number is 5,000, very large. So if the discrimination power of that term is large, okay, then that's a good thing. But we don't like this much large numbers, so we take the logarithm of it. If you take the logarithm of 5,000, it's going to be smaller, of course. Okay, 2 power, it is like 10, 12, 14, maybe something like 14. Instead of 5,000, we are going to use 14. Okay, 1 is going to be again small. So IDF of a term is going to give us the discrimination power of a term. And for each document, we have the term frequency. So the logical thing is, if you multiply the term frequency I of a term times the inverse document frequency I, that will give us a very good indication of a term for that document. IDF I is not for document, it is for a term. TF-I is the frequency of a term inside a document. Okay? Frequency of a term inside a document. That's why TF-I, TF-IJ is for document J, okay? So TF-IJ times IDF-I. There is no J's in IDF. Okay, so we multiply them. TF-IJ times IDF-I, okay, which is this one, is a very frequently used weighting method to express a document, in real valued vectors. Okay, so experimentally this works very well. There have been many other ways of expressing documents, but TF-IDF weighting is typically used a lot. It is known that it works very good with the web pages and that kind of stuff. Okay, any questions so far? Nobody's asking me any questions. Maybe I should ask questions a few bit. Okay. Okay, let me go to my that way maybe I can take the attendance too. Okay, Aras, could you tell me why we don't have a J value under the IDF? TF has I and J values, but IDF doesn't have anything. IDF has only I. Why don't we have a J value for IDF? Aras Topuz.
Hocam kaçırdık sanırım.
The question is,
Yok, soruyu anladım da.
you talk in English, not in Turkish.
Sorry. Probably I missed it. I can't say the...
But I ask you, if you have any question, just ask me the question. I just told you what it is, and I'm asking you back again. So let me ask you another question. Why didn't you ask me the question that you did not understand what I said? Okay, Büşra, your turn. Büşra Yılmaz. Tell me why we don't have J under IDF. Büşra, are you listening? Büşra, are you listening to the class? I guess Büşra logged in and she left. Maybe I should kick her out. Because she is not in the class. Okay. Let's go to last night A's or B's or okay. Murat Beyaz. Murat, could you tell me why we don't have a J under IDF?
Because in IDF we are checking for all documents, not for a specific one.
Exactly. Because for the IDF we have only the terms, not the documents. IDF means inverse document frequency. Okay, so we are talking about how many times this term has happened in the whole document set. Term frequency is how many times this term happened in a specific document. Okay, that's good. Okay, thank you, Murat. So let's move on. Let's look at this similarity measures again. Let's say I have represented my documents. With TF-IDF mechanism like this. For each document I prepared this, and these are very large vectors, and I like to find the similarity between my query vector and my document vector for J. How am I going to do that? Okay, similarity measure is something that's studied a lot, and we are going to look at a few examples of it. One way of doing this is cosine similarity. Let's try to remember what. Let's say I have two vectors. Okay, A, B, C. This is vector 1, simple three-dimensional vector, and D, E, F. If I multiply this using the dot product, so what I do, the dot product of two vectors, let's say vector 1 dot vector 2, it is A times D plus B times E plus C times F, right? This is the dot product. Okay, so I know that the dot product is good for measuring the angle between two vectors. Okay, I know that from my mathematics knowledge. Why? Because if you multiply two vectors using the dot product, it will give me the cosine of the angle between these two, cosine of the vector between these two. It is like v1 vector dot v2 vector is the same as the length of v1 times length of v2 times the angle, cosine of the angle between these two vectors. Okay, so if these two vectors are orthogonal, if the angle between them is 90 degrees, then this cosine alpha will be 0. So I would get 0 out of this product. Let's say I have two vectors, 1, 0, 0 and 0, 1, 0. Okay. If you think about them in a three-dimensional world, these are orthogonal vectors, right? These are orthogonal vectors. The angle between them is 90 degrees. And if I multiply them, what am I gonna get? I will get 0, 0, 0, and I will add them together. Okay. And I will get 0 out of it. So the multiplication of these two is 0. And another feature of dot product is this one produces a scalar value, right? Scalar value. Okay, it's not a vector. The result of a dot product is not a vector, but it's a scalar. So if the angle between these two vectors is 0 degrees, then this cosine will be 1. If the angle between them is 0 degrees, then that cosine is going to be 1, and this product is going to be large. Is going to be large. That's what it says actually. If you multiply a query vector with a document vector, that's what you're gonna do. Multiply it between them. Okay. So this is all the terms of the document number J and all the terms of query, multiply them and divide them by the length of these two vectors, and that's going to give you the cosine of the angle between them. Okay, so this is called cosine similarity measure. Since it's a cosine can change between -1 and +1. So +1 means they are very, very similar. Okay, 0 means they are orthogonal. -1 means they are similar in a way that they are just the opposite. Okay, they are similar in a way that they are just the opposite. But how can you... Okay, question for you. We said that this one would produce values between -1 and 1. Right? That's what we said. Is that correct? Because that's going to give me the cosine of the angle between two vectors. Cosine of the angle between two vectors can be 1, can be 0, can be -1, or anything in between, right? But given our circumstances, this is what we are doing, right? To find the angle between two vectors of two documents. What would be the range of this formula? It would be between -1 and 1, or it's something else? Let me tell you something. I mean, it cannot be 1.5 or 2, because this formula will never give you anything larger than 1 or smaller than -1. Okay, anybody take a guess?
Sir, it couldn't get a negative value, I think.
Yeah, that's correct. Why? If you look at the formula here, just look at the formula. What does the formula say? Multiply the TF-IDF values of the document terms and the query terms. Okay, if I multiply those values, but those values cannot be negative, right? I mean, how are you going to make this value negative? Because I only counted, okay, I am only counting the frequencies of the terms. or the frequencies of the documents. There are no negatives, right? There are no negatives in there. So there is no way any of these values could be less than 0. They could be at least 0. At largest, it is 1 point. Largest it could be very, very large. I don't care, but it's going to be all 0 or positive. So for our case, all the values are going to be between 0 and 1. That's why this picture is a right picture. Okay, no component of this D1 or D2 is going to be less than 0. They are all greater than 0, equal to 0 or greater than 0. So it looks like...
May I ask a question?
Sure.
Can we say that since we are making our calculations with the distances of these vectors, and distance cannot be negative, so can we say that, basically?
Well, yeah. But I mean, in order to say that, you need to show that your formulas doesn't allow any negative values. And since we verified that our formulas cannot produce any negative values, only the values between 0 and 1, we could say that this is a very good metric to measure the distance between, or the similarity between, two vectors. Okay?
Thank you.
Can I ask a question, sir?
Sure.
So, let's say we have another D3 with the same direction as D2.
Yeah.
But it
It's
is
like, yeah, you mean like that, right? Like this.
Yeah. So, then there is no difference with the results of D2 and D3.
Yeah, exactly.
Is it something bad?
No, actually, I mean, let's try to see what... Okay, give me an example where this can happen in terms of documents. D2 and D3, they have exactly the same direction, but their lengths are different. How could this happen? Let me tell you how could that happen. D3 is the same document as D2, but I copy-pasted the same document 2 times. And the frequencies of all the things are happening more often. Something like that, right?
Yes.
So I mean, I would say that these two documents are very similar. Okay? When I am making a comparison between different documents, what I'm saying is that, okay, these two documents are containing the same information. One of them is repeating itself more, but they contain the same thing. Okay?
Okay.
And frankly, I don't think that that's going to happen a lot because I have this normalization stuff here. Remember, I normalize all the term frequencies by the maximum number. Even if that happens, it's going to be 1.0 for both of them. And the term frequencies are there. We are not going to see that kind of picture, actually. Okay, we are not going to see that kind of picture. But, I mean, those two documents might be very, very similar in terms of angle, but their length could be... I mean, this is what we are doing. See, I am dividing them by the length. These are the length of the vectors. Okay. So, how do we know that this is a good similarity measure? Okay, it produces numbers between 0 and 1, and our experiments shows that this is a good similarity metric. What kind of experiments are there? They're all controlled experiments and experiments done on the human beings. Maybe 20 years ago, no, 30 years ago, no, 25 years ago, Google was there in 1996. Yeah, I think 1996 or 7. Google search engine was there, and the Google's first search technique was based on this. Okay, and people like this a lot. Why? Because if Google says that this is what you need, okay, this is what you are searching for, mostly you get a hit in the top 5 or top 10. all the other search engines, they fail to bring larger numbers or better numbers. Okay, so I know that this used to work. Later, of course, I mean, when you are doing this, okay, it is very easy to break this one. Why? What would you do? You would put in your document, under your document, if my search engine uses this idea, okay, so it is easy to hack it. Why? What would you do? You would put lots of terms under your documents, hide them, okay, so your document is going to have lots of terms happening in it, and artificially you are going to be similar to many things, okay, similar to many things. So they had to come up with other ways of working around that hack. Okay, so this is good. Okay, this is good. Let's talk about this idea. This philosophy says that you will know a word by the company that it keeps. So far what we did was let's try to match the words itself. But this guy says that a word is okay, should be representable by the context of it. Okay, what do you mean by, I mean, here what we did was, I mean, if the word student, or remember the perplexity, if perplexity happening only 1 out of 5,000 documents, then it's an important word and I should match it and etc. That's what I was saying, right? But this one says that, I mean, the same word can mean many things. Also, to mean the same thing, I use many different words. Okay, instead of perplexity, okay, maybe I am using information quantity. It is almost the same thing. Or information per bit. These are all similar things. I am not using the same term, but different terms. So the context of these terms are similar, but how we spell them, the letters in those words are different. So in order to match these kind of situations, for example, if let's say I am trying to get a job, I am making a search, computer engineer or software engineer. They should be very, very close, right? And instead of computer engineer, if somebody is giving me a software engineer document, that's acceptable. But computer and software are two different words and their terms are different. Our method of representing documents or terms is not going to work. So how am I going to do that? So they are suggesting this distributional semantics. Each word should have a distribution, statistical distribution. Okay, something like that. Okay, these are the words. Okay, word number 1, number 2, number 3, number 5, number, okay, it goes like word number 40,000. Let's say I am looking for this software. This graph shows me that the word software happens a lot with this word. Let's say this is computer, and it happens a lot with this word. Let's say this is compiler, but it happens very little with this word. Let's say dog. Okay, so this is a occurrence distribution for word software. How would you derive? Okay, let me use a different. Okay, blue means software. I like to draw the same distribution for another word, okay, let's say computer, okay, it's going to be very similar, something like that, okay. So the distributions of the software and computer are very similar. The idea is instead of using the frequency of these terms, let's use the context distribution of the terms. So vector space, distributional vector space, lexical semantics. Okay. So dimensions encode aspects of the context in which the word appears. How often it co-occurs with another specific word. Okay, so and I'm going to do the similarity measurement using maybe the same cosine similarity thing. So we will not maybe use the same term frequency, inverse document frequency, but we are going to use this idea. Let's find the friends of that word. Okay, let's find the enemies of that word and use this information to represent that word. If two words are semantically similar, then that information should be similar. That's what we're going to do. Okay, so let's say I have, remember, okay, so this is, let's say this is here 1.0. This is 40,000 dimensional vector. The values change between 0 and 1.0, maybe like that. Okay, 1.0. So it's a 40,000 dimensional vector. As I said, it is not a very easy thing to visualize it, but let's say our vectors are two-dimensional, not 40,000 dimensional, but two-dimensional. If I have represented my words in two-dimensional vectors, context vectors, and put the word rock, okay, this is dimension 1 and dimension 2. This is what you would expect, okay? You would expect that the vector for cup and bottle and water should be close together, okay? The vectors of dog and cat, the vectors of woman and man, and the vectors of computer and robot, they are all together. So this is sample lexical vector space. You do not expect this kind of distribution, okay, this kind of picture from the TF-IDF representation, because TF-IDF representation is just tries to measure the frequencies of documents, frequencies of terms inside the documents. Okay. Osman, I don't hear your voice. Are you asking a question? I know my question is, my voice is fine because I get my closed caption text. Okay. Okay. Anybody has any questions so far? Anybody has any questions? Let's take 10 minutes of break. After the break, we will continue. So it is 14:33. We will be back. 14:33. Okay. So sample lexical vector space is like that. Simple word vectors, if you are using this technique, the distributional semantics, okay, for a given target word, we create a bag of word document. That means that we find all the words that co-occur with the target word in a large corpus. Okay, so let's say I have this word, okay, and I have, let me use different color. Okay, this one. I have I take the word before and the word after, 2 words before and 2 words after. These 4 words are the context words for the center word. Okay, so that's what we do. Window of k words on either side. K in this case is 2. Okay, and all words in a sentence or paragraph or documents, we can do that too, but usually we have this kind of case. Okay, for each word, create a TF-IDF weighted vector from the document for that word. Okay, again, we are doing the TF-IDF, but we are doing in a context-wise way. Okay, and then we are doing the semantic relatedness of words using the cosine similarity. So we are doing the TF-IDF in a way that, okay, TF-IDF in a way that we do the frequency counting within this fixed windows, okay, and we use the resulting vector. To represent that word. Maybe I should stress this out. We did not represent words using the TF-IDF vectors, right? The TF-IDF words, we use them only to represent documents. So what we are doing right now is, for each word, wherever we see it, we take a window around that word, and the word is at the center. So we form a TF-IDF weighted vector for that word. Okay, so we treat each word like a document. Okay, so this is one way of representing a word using its semantic relatedness. That will be a better representation, much better than counting just the term frequencies. Okay, so maybe we can go a step further and we use maybe other contextual features. For example, if we do the dependency parsing of a sentence, now I know how this word is connected to the other words. This one is object. This one is the subject, etc. This one is the determiner. They are connected, right? So I know these relations. If I know these relations, I can do syntax dependent context features. Okay, age label dependency parses, and then I can do the same thing. So both context and the syntax will be included in my word representations. Okay, so I will skip this one. This is just another feature weighting stuff. I mentioned a number of times that our vectors will be very, very large. I mean, this 40,000. Where does the 40,000 come from? It comes from the number of terms in our vocabulary. And 40,000 is not an exaggeration. Sometimes it is larger than that. Sometimes it is 200,000. Sometimes maybe 1 million. Because especially for Turkish, I mean, if you don't do the morphology right, I mean, we can have hundreds of forms of same word, right? So that's not good. I mean, I don't want to deal I don't want to be dealing with 40,000 dimensional vectors in my calculations. So what am I going to do? There are very well-defined dimensionality reduction techniques by the linear algebra people. One of them is principal component analysis, which can be done easily by singular value decomposition. Okay, so we are going to say that I have something like that. Okay, good. All the words, how many words do I have? How many words do I have in my vocabulary? There are 40,000 words. And each one is represented by 40,000 terms. So this will be 40,000 by 40,000 matrix, right? 40,000 by 40,000 matrix. But most of these matrix elements will be 0 or close to 0 because many words are not related. You are not going to see this word perplexity with frog in the same sentence. That will not happen. I don't think so. Okay, so there are many word combinations like that. So most of these elements will be 0. So in fact, I could say that maybe without losing much information, I could represent each word using a smaller size vectors. That's what we are going to do. We are going to reduce the dimensionality of the space by using various mathematical techniques. One of them is going to be principal component analysis. Just to visualize the idea, let's look at this two-dimensional world. Okay, this is my dimension 1 and dimension 2. As you see, all the dots, all the data points on this simple two-dimensional world is around this direction. Okay, let's say this direction is L1. If I rotate my world maybe this much clockwise by this angle alpha clockwise, okay, rotate it this way, then maybe I can project each of those points to this line like that and ignore the second dimension. So here I am losing some information, yes, that's true, but I am keeping the most important dimension, which is the dimension of L1. L1 is not D1 or D2, so I need to transform my space, D1, D2 space, into a new space where the second dimension could be ignored without losing much information. That's what principal component analysis does. Okay, you give the principal component analysis a 40,000 dimensional data, and it says that I am going to transform your data to a new space, to a new 40,000 dimensional space, but I will tell you which dimensions are most important. Okay, that's what PCA does. And you will take maybe top 100 dimensions out of 40,000. That will be good enough for you to represent your words or documents. That's what the dimensionality reduction does. Okay, that's what the dimensionality reduction does. So you will choose the K new dimensions, and K is going to be much smaller than 40,000. Okay, and PCA is doing one of them. Okay, this is the visualization of the idea. Again, I am losing some information, but that information maybe is not that important to find the similarity between two words in terms of their semantic distribution. Okay. So how would I know if my lexical semantics works fine? How would you know that what I am doing is good? Okay. I mean, this looks nice. Let me show you. Yeah. This looks nice. I did whatever, I did the algorithm here. Okay, I did the algorithm here. That was fine. Okay. After I did that, okay, I formed this graph using the PCA. Okay, this one gave me 40,000 dimensional vectors, right? And then I use PCA to drop this to two-dimensional world. And this two-dimensional world, I started seeing this. Okay. This looks nice, but how do I know that I am doing good? I mean, by just looking at pictures, nobody's going to believe you. You need to produce some numbers. And the other thing is that you cannot go back and check your data to see if you are doing good or bad. Why? Because this is all unsupervised. Why do I say this is all unsupervised? Formation of these words, okay, these word vectors, lexical word vectors, is done in an unsupervised way. Why am I saying this? Is it really unsupervised?
It seems like we don't have ground truth value, so
We don't have the ground truth vectors for any of the words, right? Yes, I mean, we don't have any labels. It is good. It is both good and bad. Why it is good? Because I don't need any human annotations, any labeled data to represent my words by vectors, right? It is good in that case. It is bad in that I don't know if I am doing good or bad. I mean, I just came up with vectors, and those vectors produce these nice two-dimensional representations, and in that representations, men and women seems to be close, cat and dog seems to be close. Yeah, that's fine. But how am I gonna know that one method is better than the other method? Okay, let's say I found slightly different method. How am I gonna compare those? So that becomes a problem. To get rid of that problem, this is what we are gonna do. Okay, this is what we are gonna do. We will ask humans to give degrees of similarity between two words. Okay, I am going to ask 3 people. Okay, tell me how close these two words are between 1 and 10. 10 is the closest, 1 is the least close. Okay, they are far away. Dog and canine, they are similar. Dog and cat, somewhat similar. Dog and carrot, kind of, but they are both living stuff. Dog and knife, no, they are not similar. Okay, so humans rate the semantic similarity of a large set of word pairs, maybe 100 words. Okay, they do this. 100 words by 100 words. Okay, of course the diagonal doesn't make sense. Okay, so this is dog, cat, knife, flower. Dog, cat, knife, flower. So I give this matrix, and they said, okay, cat is similar to flower, maybe 3. cat is similar to, I don't know what this is, knife. No, it is not similar, it is 1. So I get all of these values. Then I do my vector space formation. For each word I have my vectors, and I do my similarity check using the cosine similarity. Okay, and that similarity, if it is good, then I am fine. Or I mean, if it is not that good, then there should be problems. Of course, you don't expect, let's say this is person 1 and person 2 does exactly the same thing. Okay, and you don't expect person 1 and person 2 to give you exactly the same thing. You would expect that they will be slightly different, right? For example, this 3 is going to be 5 here, this 6 is going to be maybe 7 there, and this 10 is going to be maybe 8. So you would say that these two people are not in agreement. There is some similarity and there is some differences between them. So you don't expect 100% agreement between human and human. Also the same is valid. You don't expect 100% agreement between a person and our computer system. Okay, and our computer system, because I don't have the ultimate ground truth for any natural language processing task. Okay. By the way, you took the ALES exam, right? ALES exam, or anybody took the TOEFL exam? Did anybody take the TOEFL exam, test of English as a foreign language? I am not going to ask you your grade. I'm just asking you if you take it. So Nida took it. Nida, you know these kind of questions. Maybe we have the similar questions in our ALES exam too. They ask you this. Okay. Find the synonym for this word, detest. Which one is most similar? Okay. Hate, argue, discover, or reveal. Which one is it? Is it argue? Is it argue? Dislike, hate. It's okay. It is hate. I didn't know that. Okay. This is how you study your TOEFL exam. You find these kind of rare words and you try to find it is just the opposite meanings or the synonyms or similarity meanings, etc. So they did whatever I mentioned to you. Okay, they given a, let's say, Wikipedia, they took the Wikipedia dump for English, okay, and they formed the vectors for all the words like the detest or hate or argue, discover, reveal. Okay, when the question comes, they just measure the vector difference between this one and all the other choices, all the choices. Okay, all the other choices, and they show that the LSA or the PCA method, that is the dimensionality reduction method, along with the distributional semantics methods, they pass this exam. Okay, so they are not saying that it will answer all the questions correctly, but it will get a good grade, better than maybe most of the humans, at least better than me. Okay, so this is all done. This is interesting, very interesting. This is all done in an unsupervised way. Okay, you learn the context, you learn the vector for a given word, for all the words, and you measure the similarity, and for the synonymity test of the TOEFL exam, you get a passing grade. Okay, good. Okay. One thing that we did not care, that we were not careful about is this. Our semantic representation of a word thinks that a word like, for example, a word like bank has a single vector of maybe 300 dimensions. There are, okay, W1 to W300. But the word bank has at least 3-4 meanings. So what was our argument? We were assigning a vector depending on the meaning of this bank, right? By looking at the other words around it. So this is in conflict with what we are saying. I mean, if word bank has different meanings, then it shouldn't have a single vector, right? For a different meaning, it should have different meanings, different vectors. That's what we're gonna look at right now. Any ideas how we can achieve this? Previously what we did was we took all the sentences that includes bank in it, and using these words, these 4 words, of all the 4 words, okay, we came up with this, the vector for bank, semantic meaning for bank, okay. So 300, after doing the PCA, we get a 300 dimensional vector for bank. But now I am saying that the word bank has many different meanings. There shouldn't be a single vector for it. How would you handle this case? What would you do? Any ideas? I mean, in one meaning of bank, it's the financial institution bank, okay? So one financial institution. The other one is the bank that we sit on, right? We sit on banks. It's like a seat. Usually you see it at the parks, okay? The other meaning of bank is just the sides of a river, okay? Banks of a river, you would say that, right? So that's the third meaning of bank. And if you look at the dictionary, I'm sure you're going to see many other meanings. To bank something means that to save something sometimes. Okay? So I like to be able to assign different vectors to each of them. It looks like I will have to do it in a supervised way. I mean, find the different meanings of bank and label them one by one, but I don't want to do that. No, I don't want to do it in a supervised way. Any ideas? Doğancan, you just tell me something. How will you do this?
We can split the bank into multiple vectors using the other verbs.
How many vectors for bank?
It depends on the word correlation. If you have finance and other words similar to financial words, then we can create another vector for them using a threshold to how many times we are going to split the vector.
But how would you make that operational? I mean, How would you know that you are talking about financial? And as I said, you don't have a dictionary to look at, okay? And you don't know how many meanings bank has. It could be 1 or 2 or 7 or 100.
In graphs, we used to look at the cluster of nodes, and we could separate them, but I don't know how can we do it in the vectors.
Okay, so that's a good start actually. They're very similar to what you are trying to do actually. So let's say each individual occurrence has a different sense, and we are gonna say that if bank has, let's say, 3 meaning, B1, B2 and B3 in 2-dimensional space, okay, there will be words like financial institution stuff, parking stuff, okay, this is like money, interest. In this case, there are parks, trees, etc. And in the third one, river and boat. These are the stuff, okay? But how do I know that which group is which? So this is what we are gonna do. Let's say it is not doing for bank, but it is doing for bat. In English, bat has at least 2 meanings. One is the stick that you use in baseball games, baseball sopası, bat, baseball sopası. The other one is yarasa in Turkish, right? Both of them are bat. For some reason, they are using the same word for this one. Okay, the natural languages are weird, and we are doing the same thing. I mean, maybe just coincidence, just a simple word. So, how would I know these 2 meanings of the word bad, and how would I separate them? So the algorithm is this. Okay, assume each group represents a sense of the word. Okay, and I compute a vector for this sense by taking the mean of each cluster. At the beginning, I assume that there are k meanings. Where do I get this number k? Well, I mean, if anybody did any grouping, okay, unsupervised learning, you would tell that we will try different k's, whichever is producing the better numbers, and we are gonna do that. Okay, so at the beginning we will say that there are k meanings of bat, or 2 meanings of bat. Okay, and you don't know which meaning it has for each occurrence of bat. Okay, so you treat each occurrence differently. You're gonna say that, or let's go to the example of the bank. You're gonna say that, okay, I have 100 occurrences of bat, and for each one I will form my own. Vector representation. So there will be 100 vector representations for bat, and some of them will fall around this area, some of them will fall here, some of them will fall around B3. Okay, so that's then after that I will run this clustering stuff, first cluster, second cluster, and third cluster. So the clustering techniques will give you how good the clustering is. If 3 is not good, let's try 2. If 2 is not good, let's try 4. Let's try 5, and that will give you the most plausible k number k. Okay, so you are not out of options if you like to do the meanings of the same word. Again, I can assign different vectors for each different meaning. Okay, sense induction. So in this case, it gave, one is for the baseball related bat, the other one is flying mammal related bat. Okay, so do I want to do this? No, I think I don't have. I mean, I can even do this specialization if I have the data. With the syntax augmentation, I can add syntax data later to these words by looking at the dependency parse-trees, but I don't want to go into that detail yet. Okay, so these are kind of classic approaches for vector representations. Okay, vector representations. Now I know when I say I am looking for a software engineering job, but if I am looking for software engineering job, but in my data set there is computer scientist. Okay, so the word vectors of the representation vectors of this string and the representation vector of this string will be very similar because their contexts are similar. And all I am doing is with this one are unsupervisedly. Okay, I am not doing this in a supervised way. Okay, good. Any questions about these classical approaches? Now I am going to look at more newer ways of doing stuff. Any questions? I guess there are no questions. Then in that case, let me try to show you how we are doing this. With the new techniques. Okay. And this will be our introduction to deep learning on NLP. Well, it's not going to be exact deep learning, but it's going to be a kind of introduction. I will not talk about any neurons yet, but it will be a good introduction. Okay, so the definition of meaning, okay, in Webster Dictionary is this. What is the definition of meaning? The idea to represent something, okay, the idea a person wants to express, okay, the idea that is expressed in a work or writing. So those are all definitions of the meaning. In computer science, in the computer engineering world, okay, the most of the time the linguistic, when they say the meaning, they use denotational semantics. Denotational semantics is like when you use a function. For example, how do you take, does anybody know how to take the square root of 174,357,6? Does anybody know that? How do you take the square root of it? Maybe some of you know, maybe you can give me a procedure, but in programming languages, all I do is I just call a function. So for a programming language, the meaning of a sign is the implementation of this function. Okay, that's called the denotational semantics. The meaning of that thing is the implementation. Denotational. So notation is the main thing here. Okay, that's the linguistic way of thinking about the meaning. So they started from this, and they say that in a computer, if we use the idea, what are we gonna need? And they say that, okay, we need to find a large corpora that are related to meaning, okay? How do you express the meaning? Maybe we can express the synonyms or hypernyms. Hypernyms are relationships, is a relationships. For example, a house is a building. Building is a man-made object, etc., right? Is a relationship. Synonym is the similarity stuff. Okay? So they invented this WordNet. WordNet is a human-built word data set. It has lots of relationships between the words. For example, what are the most similar words to word good? Just tell me the similar word to good, okay? It's going to give you that. Or give me the hypernyms for panda, and it's going to give you that. For these are Python code. Okay, it says that from import WordNet as WN, and under the WordNet I am going to find the synset. Synset is the classes of this panda, and give me the hypernyms of this panda. Okay, it says that panda is a prochyonid. I don't know what it is. Carnivore, placental mammal. I know that mammal. Mammal I know. This memeliler, omurgalı. Chordate, I don't know what it is. Then animal, organism, living thing, whole, object, physical entity, and entity. So it goes all the way. Everything in WordNet is an entity. Some of them are physical entity. Some of the physical entities are objects. So there is a relationship between them. It goes like that. Okay. And in this side, okay, I want to find the similarity. Okay, format pauses, synset pause. Okay, it wants the part of speech, labels of all the pauses, and it likes to find the similarities between them. Okay, what is similar to good? Synonyms. Okay, goodness. See, the good has a different meaning here. Commodity. In commodity there is a good. Okay, for the adjective, good could be an adjective. There are other stuff, beneficial, estimable, etc. For adverb, again, good is an adverb, and similar adverbs are there. So if we have such a data set, we can do the similarity task. Maybe remember, what did I say? I am looking for a computer engineer job, but I like software engineering jobs to come back. Okay, maybe if I look up the similar words under the WordNet, it's going to work. So just use the WordNet. WordNet is very large. Millions of words are there. Okay, millions of relations are there. Just use the WordNet to make this kind of lookup. Find the similar words, also the hypernyms and the other kind of relations. Do this kind of search, but this is problematic. Why is this problematic? Because, okay, it is great, but it is subjective. Humans did it. Okay, it is done for English, but we don't have it in Turkish, and we don't have it in the other dialects of Turkish, such as Azerbaijani or Uzbekistan Turkish, right? And exactly, it doesn't give us any vectors. I cannot make a vector out of WordNet. Okay, and when you get a new word, okay, people make up new words. For example, for good, okay, they started using for the last 10 years, okay, vect, okay, nifty, wizard, badass, bombast, okay. I think Trump made up a few words for good. So it is impossible to keep up to date with the did you see, are you saying, oh no, okay, maybe you're gonna see it from the maybe you are saying it from the, you're gonna see it from the recording, but the closed captioning, automatic closed captioning censored most of the words that I told a few minutes ago. You're gonna see it. So it is not that good. So we want everything, most of things to be unsupervised. Coming up with unsupervised vectors is a much better thing. Okay, one way to express vectors, maybe one stupid way to express vectors is this, one hot vector. Well, this is not used actually, but it's going to be important when we started assigning vectors automatically using the neural methods. Okay, so let's say I have a very large binary vector, and this is the vector for motel, and this is the vector for hotel. Two different vectors. The only difference between them is, okay, these are one hot vectors. One hot means that out of all the dimensions, there is only one. There is a single one only. Okay, so the one that corresponds to motel is this one. The one that corresponds to hotel is this one. Okay, so this is one way of representing words by vectors, but it's not a very good way of doing it because the dimensionality of these vectors will be very, very high. It's going to be maybe 40,000. Again, the number of terms in the dictionary. And similarity is not there. I mean, motel and hotel should be very similar, but I don't see any similarity. I mean, if I take the difference between them, the difference between hotel and motel is the same as the difference between hotel and the cat, right? So that's not going to be good. I mean, this one hot vector is simple, but it's not good, and it is as useless as the TF-IDF representation for a single document. It doesn't know anything about the similarity. Okay. So if somebody is looking for Seattle motel, but all I have in my dataset is Seattle hotel, it's not going to find it. It's not going to find it. So again, this guy, this saying, you shall know a word by the company it keeps. Okay, one of the most successful ideas of modern statistical NLP. Okay, I am going to use the context word of this banking. Okay, it looks like whenever there is banking, all kinds of system, okay, Europe, unification, government, crisis, etc. These are all happening. So the accompanying words are very good information for the context of a word. Let's use this context to represent it. Okay, you might say that we already did that, but we are going to do it in a different way right now. We are going to do it in a way that this banking has a word vector, okay, that represents it using these real values, and we don't want to represent it using 40,000 dimensional vectors or 500,000 dimensional vectors, but we like to do it like maybe 100 dimensional or 200 dimensional vectors, smaller vectors, not very large vectors, but smaller vectors. But in this case, I am not going to use any principal component analysis. All I am going to do is I am going to feed that information, unsupervised information, to my neural network, and I will get these results back, and they will be immediately usable. Okay. Sometimes in this word, the word vectors are word embeddings or word representations. And again, they are distributed representations. Why? Distribution, because we look at the distribution of the context words of a given word. Okay. Again, once I do that, two-dimensional visualization is going to be something like this. Something like, I don't know what's happening. Let me go a few slides and come back. Go a few slides. Anyway, okay, here it is. Okay. So the similar words have similar positions in this two-dimensional word. Two-dimensional word. Okay, this is what you're gonna do. So we are gonna look at this work, Mikalo and others in 2012-13. This was hugely successful work. It's called word2vec. You produce vectors out of words in a fully unsupervised way. Okay, we have a large corpus of text, for example the Wikipedia dump of English words, and each word in a fixed vocabulary is represented by a vector. Fixed vocabulary. Okay, and we say that we are gonna go through the whole text, the whole 1 billion words of Wikipedia, large corpus. Okay, we are gonna go it one by one, and we are gonna say that, okay, let's say this is my center word. Okay, I usually like yellow flowers. This is the center word. These are the context words. So the red is the center word. Okay. Blues are the context words. And then we are going to say that find the similarity between the center word and the context words. And I'm going to say that if a word happens in the context of another word, these should be similar. Okay, use the similarity of word vectors for C and O. C is the center word. These are the context words. Center and context. And we are going to calculate this probability. And while we are doing this, we will keep changing the probabilities of seeing them together. If I see like and flowers a lot in the same context, we are going to say that the probability of seeing like and flowers is large. If I don't see it, then the probability will be smaller. Okay, that's the idea. That's the idea. Okay, so before I continue further, maybe I should take 10 minutes of break. After the break, we will continue with the details of this word2vec. Okay, 10 minutes of break. Let's be here around 15:33.
Bu bazen çalışma olmuyormuş. Öyle mi? O toplam 10 senesi. Ben aynı zamanda olmuştum ya. Bir daha olmak istemiyorum ben ya. Bu şeye benziyor. Unutmuşum her şeyi ya. Bizim arkadaşlardan bir tanesi bir şeye katılmış. Çin aşısının şeyde böyle. Artık ben olmam falan diyor. Doktorlardan bekliyor. Oğlum dedi. Manyak mısın? 3 diye birine şey veriyorlar dedi. Onu ben soruyorum. 3 yaşından ikisi normal açıyor. Hiç riske girmedi. Bilmiyor evet. Bilmiyor. Önemli değil. Niye anlamıyorsun? Artı bir de ama 31 mi ne var? Aktif olması. Hemen olmuyor. Tam bir başka bir sorudan bir şey. Allah'ım nasıl göreceğiz ya? Yine beraber bir şey. Yine bir defa şeyden aslında kesinliği var. Bazen bir şey çıkıyor. Hocam bizim oradaki camide adam ikide bir şey yapıyor yani. Tek kişi demiyor. Şu 3-4 kişi gidiyor. Sürüyor. Ben böyle bir şey yapıyorum. Önce okupasyonlar geçiyorum. Bir hafta. Nasıl çocuk? Kendisinden kızmış. Ben artık hepsini takip etmeye başladım. Şimdi bakıyorum. İngiltere'deki şey olan yeni bir tane çıkarmışlar. Mutasyon geçirmişler diye. Daha öldürücü değilmiş ama daha farklı. Ya bizde var mı? Ben size göre çok daha önemli mi? Yazık bir benim geçirdiğim şeydi daha efendiydi. Burada bir vardır ya. Ben dedim ki şey geldi mi aslında hocam? Onu görüntüler yaptım hocam. O kadar şey değil hocam. Odasının zor oldu. Hatta içine giremedim. Bir daha atamadım.
Okay, let's move on. So that's the idea. We are going to use the probability calculations of the probabilities, and we will keep adjusting the word vectors to maximize this probability. Slide up. Okay, let's take this sentence. Problems turning into a banking crisis as, okay. So remember our window is of size 2. We are trying to calculate, okay, this is the C, okay, this is O, and O, center and context. Okay, so these are the probabilities. Given WT, what is the probability of banking? Given into, what is the probability of banking? There is a probability. Given crisis, what is the probability? No, given into, what is the probability of crisis? Seeing, okay. So it looks like if I am seeing these words together, a lot, this probability should be high. That's what I'm saying, okay? If I am seeing these together a lot, this probability should be high. If I don't see them, this probability should be smaller. And I'm going to repeat this billions of times. How many words do I have in my corpora? Billion word. And I'm going to repeat this a billion times. That's what we're gonna do. And I did this for into, and I am doing this for banking. And I will step one more. I will move over to the right, and I will keep doing this. Okay, so try to compute this probability, and at the end, I like to maximize this multiplication. This is a very large multiplication actually. From 1 to t. T is 1 billion. Again, it's very large, 1 billion. And what is m? Tell me the typical numbers for m. Somebody tell me a typical number for m. I know you heard me because my closed caption says exactly what I am asking. Mustafa, are you going to? Okay, Nida is saying 2. Yeah, it was 2 in this case. Of size 2 and of size 2. So it says that, for position t, okay, m is going to be t minus 2 from, okay, it's going to be, j is going to change from t minus 2 to t plus 2, okay. So all these probabilities given, in this case, given banking, what is the probability of crisis times giving banking the probability of as, giving banking probability of into, giving banking probability of turning. So they all will be multiplied together. Since I have seen them for all the corpora, I will do this, and I like this to be very large as possible. What are the theta are the parameters of this calculations, and we are going to see it in a few minutes. Usually we don't want to multiply, since these are probabilities, they are between 0 and 1, right? Between 0 and 1. If these numbers are close to 0, this multiplication will be very small, so it will underflow. We don't like that. That's why we say that let's take logarithm of it, and put a minus in front of it, let's minimize it, okay? When we take the logarithm of the whole thing, what is the logarithm of a times b? Of course, it is a plus b, log a plus log b, right? So it turns into an addition operation, and with the addition operation of small numbers, there will be no underflowing, okay? We did this trick a number of times. So I take the logarithm and I do the addition instead of doing the multiplication. So our objective function is to minimize this j theta, and theta includes all the system parameters. And what the thetas are exactly, we are going to see it in a few minutes. But I am mostly now wondering about this p. How should I calculate this p? How should I calculate this p is going to be important. Well, you will not be surprised because you will not be surprised because you're gonna see that we did something similar before. Okay, so our objective function is this. For this large t value, do these calculations and multiply them. How do I calculate these? Okay, we will use 2 vectors per word. Okay, remember the picture that I'm going to draw it again. Center, context. Okay, what did I say? Given the center, what is the context probability? That's what we are trying to calculate. But the center word could be sometimes center word, sometimes the context word. It changes. Okay, so for this word2vec calculations, they made this decision. They say that for each word there will be two vectors. Okay, the vector one will be uw, okay, or vw when the w is the center word, and uw when w is a context word. Okay, so to calculate this, given the context, given the center word, what is the probability of context word? To calculate it, we are going to use this calculation. I mean, it might look a little bit complicated, but it is not actually. It is not. It says that multiply dot product of the center word and the context word, their word vectors, okay, that's it, and take the exponential of it. So I am going to take the exponential e to the power u times c. I take the transpose of it just to make a matrix multiplication. So this is my vector. Let me draw it here. This is my vector UO, and this is my vector VC. You cannot multiply these directly. So what I am doing is I am taking the transpose. Take the transpose like that. Okay. If this one has 100 elements and this one has 100 elements, multiply each of them and add them together. So that will be a dot product. So E to the dot product something. Remember when I ask a question, what did I say? If I multiply the vectors of two documents, remember the TF-IDF representation? Somebody told me that out of TF-IDF representation multiplications, you cannot get a negative value, right? Can I say the same thing here? No. Why? Because my vectors are not restricted anymore, because I was doing some counting in that case. Now I am not counting, okay? So my vectors could be any value, including negative values, positive values, and 0. That's why, since I am going to calculate this probability, and the probability are supposed to be less than 1.0 and greater than equal to 0, right? I need to make everything positive. So if I take this exponential of e to the power u0vc, like that, it's going to make it positive. And this below part is going to be positive. So what is the graph for the e to the power x? It's going to be like this, right? E to the power x. E to the power x. So e to the power 0 is 1. E to the power 1 is e. This is 1. So e to the power minus infinity is 0. It goes like that. And what is the nice property of this graph? We say that at this position, e to the power 1, okay, is the same as the e. So that's why we say that the derivative of e to the power x is the same stuff. E to the power x is the only exponential function that has the same derivative. Okay, good. So do you understand the lower part? What does the lower part say? The lower part says that the upper part says that multiply the word vectors of context word and the center word, right? The lower part says that multiply the center word vector with the whole vocabulary, that is the 40,000 vectors, okay, and add them up. Since this product, let me make this a little bigger. Since the upper part is just one of them, this cannot be larger than 1.0. It could be at most 1.0, because the lower part includes the upper part. Okay? Since both upper part and the lower part are greater than 0, this cannot be smaller than 0. So I achieved what I wanted. This calculation is going to be, this estimation is going to be between 0 and 1. So I am using almost the same thing. I am looking for the similarities. So let's go back to this one and let's try to understand it. What does it say? It says that if two words are seen together, one is a context, the other one is the center, okay, then their probabilities, given the center, the probability of the context, should be large. Okay? So maybe I should ask you this question. What happens for all the vectors, for all the u vectors and the v vectors, if I do this? They are all ones. Okay? And this one is all 1. So if I multiply two vectors, okay, together, like this one, that one, is going to be very big, right? Large. So am I And this is going to be as large as possible, because whatever the words are doesn't matter anything. It's going to be large, right? What is the problem with this? I came up with this idea that assigns the vectors, word vectors, the same values, ones. When I do that, the similarities between all the center words and all the context words will be very large, right? And maximization of this thing, or the minimization of this thing, will be at a very good level. So we are trying to minimize it because there is a minus sign in front. Am I doing a mistake? So, I mean, that doesn't make much sense, right? I mean, if I assign the same numbers to everything, all the word vectors are going to be the same. That doesn't make much sense, but the calculations are showing it that way. So assign the same values for all the vectors. Anybody has any ideas? Any ideas? Well, since this is a very famous work, this shouldn't happen. So what prevents me from doing so? Just say something. It is not that difficult. Doğancan, I am coming back to you. Okay. When I say Doğancan, it says dungeon in the closed captioning. Doğancan, tell me something. Now Doğancan is gone too. He's not here.
I'm here, but I don't know really.
You have no idea?
Mhm.
Anybody else? Ozan, do you have any ideas? Ozan, do you have any ideas? What's happening now? Why nobody's answering me? Yusuf, do you have any ideas? What prevents me from assigning the same vector to all the words?
I'm listening, but I don't have any idea.
Okay, the problem is the lower part of it. I mean, when you assign the same vector to all the words, it makes the upper part larger, but also, okay, it assigns the same thing for all the vectors, so the importance of the upper part becomes smaller. So you shouldn't do that. You should only assign appropriate values for the center of context word so that the upper part is large, but lower part for all the other vectors should be small so that this product is high. That's going to maximize it, so the minimum is a smaller value. Okay, so that's the idea. Don't forget about this formula. This is called. Do you know what this is? Do you know what this formula is called? Anybody? Anybody knows this formula? Anybody took the deep learning class or maybe neural networks? This is called softmax function. Softmax function is used in many places in neural networks or deep learning. It is used for assigning probabilities. Okay, assigning probabilities to this kind of stuff. As you see, if you like to assign stuff between 0 and 1, okay, 0 and 1, and this is what you do. And the other nice thing is, if I add up all the probabilities P given C O I, and this is OI, all the OIs, the result will be 1.0. Okay, and this is evident from this formula. These are nice properties. Softmax, we are going to use this a lot. We are going to use this a lot in deep learning world. Okay, good. So word2vec objective function is this one, and underneath there is this dot product multiplication, and I use e to the power of it to make it a positive number, and by this division I like to make everything between 0 and 1.0. That's a probability. So I should come up with vector values so that this logarithm, this probability assignment is large, so that this negative makes it as small as possible. How am I going to do it? I will do it in a few minutes. I will show you in a few minutes. Okay. So I am trying to calculate this one given into what is the probability of having these problems. Okay. So remember, there is this theta stuff, the parameters of this whole system. My parameters are this. My parameters are the vector of the problems and the vector of into along with the other parameters. So in order to calculate these probabilities, I need those parameters, and those parameters will be assigned by myself. Okay, this is kind of explains what I have told you so far, the central idea inside this one. Okay, so the dot product compares similarity of center word and the context word. Okay, larger dot product, larger probability. That's the same idea. Larger dot product means that the angle between the vectors of these two are smaller. Okay, 2, this exponential makes everything positive. 3, I normalize over entire vocabulary to give probability distribution. So this produces a probability distribution. Okay, by probability distribution, I would have something like that. Okay, so these are all the words, and this probability POC. Okay, given the context word, okay, this will be my probability distribution. The area under this is going to be 1.0. That's why we call this distributional semantics. Okay, so this is an example softmax function. Max because it amplifies the probability of largest xi. Soft because it still assigns some probability to smaller xi, whatever it is, I will assign something to it, because it is composed of multiplying two vectors, and those vectors are not zero, and I don't they will not make it zero. Again, it is frequently used in deep learning, and we will see this over and over again. So the idea is, how are we going to find those vectors? How are we going to find those vectors? Okay, that's the idea. And let's look at this function. How many parameters do we have? Again, let's say I have 40,000 words. Each one will have two vectors, and in each one there are, let's say, 200 values. So these are the number of parameters that we like to find for the whole system. And I like to minimize this formula. And I need to find 40,000 times 2 times 200 values, so that this is minimum. So this formula is minimum. That's what I like to find. But finding those numbers is not going to be easy. We are going to use numerical methods. Okay? One of the numerical methods that could be used is gradient descent. Gradient descent is this. Let's say I have a function of two unknowns, y, x, no, okay, f, x, xy is x squared plus 2y squared. Okay, and I like to find the position that makes this fx small as possible. I like to find it. So the idea is this: if I give x and y values, like if x is -3 and y is 3, okay, what would be the f in this case? Somebody tell me? It could be like 26 or something. This is 9 plus 2 times 9, 27, right? So that's correct. So if I move this from this position, to left, right, I don't know, okay? This is 3, 3. Okay, this is where I am starting at, okay? Where should I move to make this value smaller? So how would you find the direction to move to make this value smaller? How would you move, or how would you find the direction to move to make this value smaller? Should I make -3 smaller, or should I make this -3 smaller or larger? Should I make this 3 smaller or larger? How would you find the direction to move in this space? When you look at it here, you would say that, okay, I would move exactly in this direction, right? But you are looking at the picture. I mean, this is kind of cheating. If you are writing the computer program, you don't have this picture in your hand. Selman Yasin has a nice idea. He says, check the slope of that point and see where it is directed. Exactly. Okay. I would check the slope. And I would find the direction of the slope. Wherever it is going downwards, I will follow that direction. Maybe if I explain this in a one-dimensional way, okay, let's say I have this fx only, or f theta only. I started at this position, random initial value here, red, red, okay, random initial position. If I take the derivative of theta, okay, that derivative of theta will give me the slope, right? It will give me this tangent line with the blue. That tangent line is going to show me which direction should I move to make this function smaller. So it would tell me that, okay, if I move that direction, it will be smaller. Now I came to here. Again, I will take another derivative, another one. So every time I take a new derivative, my slope is getting smaller and smaller. When I hit the minimum, my slope is going to be 0, right? I cannot move any further. That's why when you solve this f theta 0, it will give you the maximal, minimal, local minimum points, right? So this is just a function of one parameter. This is a function of two parameters. To minimize a function of two parameters. What I am after is I have a function of theta, and inside the theta, okay, theta is an element of r to the power 40,000 times 2 times 200. So there are 80,000, 8 million, there are 16 million parameters inside this theta. This is a 16 million dimensional problem. So I am trying to find a minimum of a 16 million dimensional world. Okay, so it's going to be a difficult problem, but I have powerful enough techniques. The gradient descent works in 1 dimension, 2 dimensions, or 16 million dimensions, as long as you behave smart in a smart way. So that's what we are gonna do. We are going to take derivative of each dimension out of these 16 millions, and I am going to find the direction to move in each of these directions, and start from a random position, and I will try to take the derivative of this function with respect to those parameters, and I will change my parameters small by small at each step until I don't see any improvements. And that's at that point I will tell that, okay, this is what I tell you as the values of those vectors. Okay, again, this is my parameters. It is 2 times, this is 200, 2 times 200 times 40,000. Very large space. Okay, so I need to take the derivative of the j value, which is the negative of those summation of logs. Okay, and with respect to, I need to take the derivative of that formula with respect to each of these dimensions. There are 60 million dimensions. Okay, and we optimize the parameters walking down the gradient. And let me skip this one. Okay, calculating the gradient is going to be that way, and that's going to be basically it. How we do it. Should I go back or no? I'm not going to go back and do that thing. Some people say that why did we have 2 vectors for each word? Okay, and that's because it is easy for optimization. It is easy for optimization. I don't have to be careful about switching the words from given to the center to the context. So I treat them separately. So I have two vectors. Okay, that's one thing. The other thing is this. Why did we choose this way? I mean, given banking, what is the probability of as? Or giving banking, what is the probability of crisis? Giving banking, what is the probability of into? Okay, that's what we said. Why didn't we do giving as what is the probability of banking? Okay, so it's like I am giving you the context word and I like you to find the center word. Okay, you could do that too, and in fact it has a name. Its name is continuous bag of words. Okay, so far we did the skipgram. So word2vec has two forms. One is a skipgram, the other one is continuous bag of words. Okay, so these are two given names. If you see them, don't get surprised. They are both used together. One of them is usually I think this continuous bag of words works a little bit better when the number of words in your corpora is smallish. But usually both of them work equally well. Okay. The other thing is this. This loop is a very big loop. This loop here. Okay. Okay, this loop is a very big loop, the loop under here. Why? Because I have to multiply my WC, okay, center word, with all the U vectors of rest of the all the dictionary. That's going to be very, very costly. We are talking about 40,000 vector multiplications. And I'm going to do this for each probability calculator. That's too expensive. So they come up with this idea. They say that why are we using all of them? Okay, just sample this space. And use only, instead of 40,000, use only maybe 50 or 100 of them. Okay, it's almost going to be and I'm going to do this randomly. It's almost going to be around the same value, at least for the sake of optimization. You will not get very different results. That's called negative sampling, naive softmax, simpler training method, and it works nice. Okay, and this word2vec system is a very compact system, and in fact it has a C code of maybe 1 or 2,000 lines of code. That's it, 1 or 2,000 lines of code, and it is available on the web. You just download it. Download word2vec. Okay, here it is. I think it has a GitHub position, or does it? Google code. Oh, I'm trying to see the C code for it. I'm trying to see how many lines it has. I couldn't find it. But if you download it, you're gonna see that it's not that big. So it's very compact because all it does is trying to find those parameters. Number of parameters is large, but the system itself is not that complicated. Okay, the gradient descent, I already talked about it, and this is how the gradient descent works. At the beginning, I assign random numbers to those 16 million parameters, and then using these 16 million parameters, I'll calculate my objective function, or that J function. Okay, after that I take the gradient and I move my parameters towards that gradient. This is the gradient, right? Gradient of my function with respect to parameters. I move my parameters towards in the direction of the gradient from the old parameters in a single step. Okay, I get my new parameters now. I do my calculations and I repeat this until I don't see any improvements in my J value. So I improve my results little by little. After some hours, a few hours, I will get my parameters, and that will make my vectors. Okay, again, it is fully unsupervised, and it will give me vectors, and those vector values could be any value, including the negative values and positive values. Usually small values, but it could be any value. That's the gradient descent. Okay, maybe I shouldn't talk about this stochastic gradient descent much now. Okay, so what is the advantage of using this method, word2vec? Remember, I did the same thing with the co-occurrence matrices. Remember how I came up with the semantic representation vectors for the words previously? What is the advantage of this word2vec over the classical methods? Word2vec is more scalable. It will work with very large corpora, and it scales linearly. Okay, it scales linearly, and the results came back much nicer than what we have with the classical methods of assigning probabilities, assigning vectors to the words using the bag of words approaches. So it has a number of advantages. That's why when people saw this, they liked it a lot. And I think next week I will show you I think I will show you it right now. Some results. Okay, so word2vec produces these kind of results. Close, meaning-wise, closed words are mapped to close spaces on the two-dimensional word. Okay, so why not capture co-occurrence count directly? Okay, I think I will. Yeah, okay. Maybe I shouldn't start talking about this one. Let me give you this. Without using word2vec, if I am using the co-occurrence matrices like I did before, let's say my corpus is very simple. I like deep learning. I like NLP. I enjoy flying. Okay. My co-occurrence matrices will be in the same sentence. I and like 2, right? I and deep, I and learning 1. Like NLP, like. Let's look at this one. You understand this? What this is co-occurrence matrix. Okay. You understand this, right? So this vector can represent the word I, and this vector can represent the word flying in this very small data set. Okay. Previously we have been doing this. Of course our vectors were like 40,000 dimensional or 100,000 dimensional, but this is a very simple example. And we didn't like it at the end. Instead, we said that we are going to use word2vec approach, which is the approach of assigning those vectors so that the multiplication of the vector values will be higher for the same context words. Okay, but the advantage of the word2vec would be these. Okay, problems with simple co-occurrence vectors. I am going to have these kind of very large matrices, even though most of the values will be 0. Okay, it requires a lot of storage for the high dimensional vectors. Okay, and for subsequent classification models, it has sparsity issues and models are less robust. The results are not coming back very nicely. Okay, word2vec is the solution. That's what we did. Okay, so next week I am going to look at the differences between the co-occurrence matrices like this and the word2vec, and I am going to show you better advantages of word2vec. Also, we will start talking more about using deep learning for the NLP. Okay, I guess that's it for today. And next week we will continue from this position. Any questions? Any questions? Okay, if there are no questions, I will see you next week.